When I was a little kid, I just loved to imagine I was ripping the wiry guts out of robots. But we'll get back to wires in a second. So far, we came up with a handful of axioms, and these are important. This is where we're starting off from, and now we're trying to learn new things. Personally, I like computer science. I like computers. Why do I like computers? Well, it springs naturally from working with information and patterns. Computers, well, that's what they do. Computers just deal with information. They're extremely versatile, and they help us with automation, which I haven't talked about too much, but that's super important too. So we need something that really is able to express these and that these can express. And for me, that's just computers. I actually have one here. Here we are. I have this little computer right here, and it even comes with a little wireless keyboard. So we're gonna go from these to this. Basically, what's a computer? Well, just like our axiom, info, patterns, and rules, a computer processes info. That means it takes some information in, and it rearranges it, does something with it, and pops a couple pieces of information out. That's all computers do. If you have something that processes information, it's a computer. The idea is pretty simple. Computers are the ultimate pattern changer, but they work with ones and zeros. And we feed a bunch of ones and zeros in, and it gives a bunch of ones and zeros out. In today's day and age, computers are ubiquitous. They're everywhere. We have them in our cell phones, in our watches, on our desks, everywhere. But every single computer is made of small components, and those components, well, depending on how complex you want to get, they're made out of transistors, or those transistors are arranged into gates. And there's peripherals. We have keyboards, and we have mice, and we have monitors. All of these things, depending on what scope you're looking at, come together to form a computer. Since every computer is made out of gates, that's one thing that we're going to look at, because gates are basically the part that takes information and outputs something else. And because computers are made out of real things, it relates patterns to the real world. We're used to computers being electronic, but that means that they're actually moving electrons. They're actually taking electricity and doing something with it. They're making crystals in your monitor light up. Computers can be made out of water, and as long as it has the components and it works correctly, we're relating these patterns to the real world, just to various capacities and usually electronically. Let's go over some of the core parts of a computer. I mentioned that computers deal with ones and zeros. Well, we can represent that with blocks, different colored blocks. So we could have a yellow block, looks on, so we'll say that's a 1, or a purple block looks off, so we'll say that's a 0. Likewise, I'll have a on and an off, or a 1 and a 0, but I want different colors to represent before and after. So when we're inputting information into something, these gates, remember, they're very simple components that take one piece of information, or two pieces, or multiple pieces, and output one piece usually, or multiple pieces. Well, the simplest amount of information is just one piece of information, and that piece could be either on or off. Now, if we're translating that, you can just keep on stays on, or off stays off. So we have before and after, and we have on stays on, off stays off. Or we can flip that, in which case you have a different type of gate. This would be a NOT gate. Whenever you have something that is on, it translates it to off. Or whenever you have something that's off, it translates it to on. More interesting things start happening when you add more pieces of information. For example, if you have two pieces of information, they could both be on. One could be on and one could be off. One could be off and the other one could be on, and that's important in some cases. Or they could both be off. Just by adding another single piece of information, we doubled how many different cases there are. Each of these rows is going to be fed into a gate. Now, what pops out of that gate is going to be a single piece of information. We could decide that when both pieces fed in, out pops on. Or we could decide that when both pieces are fed in, out pops off. We have to decide this for each case, whether the inputs make on or off. If I decide that no matter what the input is, it's always going to be on, that's not really useful. Likewise, if I decide that it's always off, that's not really useful either. because the information is kind of just being destroyed. It doesn't matter what's going in, it's just going to be off. But what happens if I do this? In this case, if both of the inputs are on, they're both ones, then your output is on, it's 1. Otherwise, in every other case, it's off. Well, this actually makes the AND gate. The AND gate means that both of your inputs are on, your output is on. Otherwise, it's off. By creating different scenarios, in this case, an OR gate, you create different gates, and then you can connect these gates together, and you do that in a specific way which lets patterns come into your computer and different patterns go out. And that gets complicated real quick, so this is as far as we're going with gates. I just want you to know that they exist, why they exist. They make logical sense. You're just translating patterns, and that's what computers do. These are just simple gates. You go up to complicated gates which do arithmetic, and then CPUs, which are just a bunch of gates bundled together, but it lets you build a computer. That brings to another component of computers, rules. That's the software, or in a sense, it's how the gates are arranged to form different architectures of computers. So software is something we'll touch on too. The other thing is how do you get this information into a computer? When computers were first invented, the information was literally forced into the computer by hand. That was obviously tedious, so we figured out ways around that, or at least the computer scientists of the day did. They figured out punch cards were a way to efficiently get information in. Later on, keyboards were invented, in which case you could just tap on some keys and get information in. You also need peripherals, or a way to get the output, which is your monitor. It could be other things too, though. A printer is a peripheral. It's a way to get output because you're getting information out in the form of a printed page. That's the core of every single computer. You need the hardware that actually makes it, the rules that let it run, a way to get the information in, and a way to get the information out. Every single computer has those components. There's two faces of modern computers. As lovely as this little box is, you need actual hardware. You need wires. You need these fantastic chips that thankfully aren't that expensive today, but let you make computers. This, for example, was about $50 or so, and it gave me pieces of a computer I can hook together. It's an Arduino. You have to have actual hardware, and this stuff gets sophisticated, so you can't really just make it yourself, though you can, and that's really interesting. It's easy to buy just a simple kit that you can put together and then program. Programming, of course, is the other face of modern computers. You need ways to program your computer, and thankfully our books help with that because there's a ton of different languages. There's basics between all of the programming languages as well, though, and we'll go over that. Just like gates make up the hardware, there's pretty specific rules and patterns that make up the software that you'll use. Hardware on one side is extreme physics and engineering, and software on the other is intense math and design. Anyone can use a computer. This stuff might look complicated, but you use a computer every day. That's the high-level user part of using a computer. But anyone can program it too. It's complicated, but it's not out of reach for almost everyone. So programming is important enough, and it's the thing that I'm super interested in because it'll let us do some pretty nifty stuff and make some games. It deserves its own little series. I'm in no part a programming teacher or a programming professional, but I'm a learner, so instead of teaching you how to program, I'm going to teach you how I see the basics of programming in its own little series, and learn it with you. For the most part, I can program a little bit, and I have some of the concepts, so I might move a little bit fast. Get yourself a book and learn if that's what you're interested in, but I'll give you the core ideas of programming languages and what programming is, and we'll make some pretty fantastic stuff with it. And we'll jump into the hardware too, because I didn't buy this for nothing. Anyways, let's have some fun with this.